Hello, future engineers. This video presents the construction of the shear and moment diagrams as well as the sketching of the corresponding elastic curve. So if you are still new to my YouTube channel, don't forget to subscribe so that I will always be inspired to do more lecture videos, which is very important and beneficial to your studies as civil engineering students or even other allied engineering courses. So I hope that you will enjoy watching and you can follow the discussion and my explanations here. So here we go. Construct the shear and moment diagrams for the beam loaded as shown below. Also construct the elastic curve. So this is the given beam. So we have to divide the loads into known parts. So let's divide them into triangles, so like that. So we will call the force equivalent to the area of this triangle as F1, and of course it passes through B because 1/3 of 6 is 2, so that's 2. F2 would be that, and F3 would be that triangle. So let's call the reaction here as RB because Bx is 0, and that's RD. So F1 is 1/2 of 6 times 12, so that's 36 kilonewtons. F2 is 1/2 of 6 times 36, so that's 108 kilonewtons. And F3 is 1/2 of 6 times 36, so it is also 108 kilonewtons. So summation moment about D equals 0 to solve for RB, clockwise positive. So we have RB times 10, then minus 15 times 12, minus 36 times 10, minus 108 times 8, minus 108 times 4. 8 because this is 2 plus 6, and moment arm or F3 is 4, 2/3 of 6 is 4. So RB is equal to 183.6 kilonewtons. Likewise, summation moment about B equals 0, counterclockwise positive, so RD times 10 plus 15 times 2, then of course 0 plus 36 times 0 minus 108 times 2 minus 108 times 2 plus 4 is 6. So this is 2 meters. 4 minus 2, then this is 2 plus 4, so 6. So RD is equal to 83.4 kilonewtons. Then you have to check if summation versus y is 0 before you proceed to construct the shear diagram. So RB 183.6 plus RB 83.4 minus 15 minus 36 minus 108 minus 108, that should be 0. So let's solve the intensity of load at B. WB minus 12 as to 2 equals 36 minus 12. So the height of this triangle here as to 6. So WB is equal to 20 kilonewtons per meter. So having found that that is 20 kilonewton per meter, first let's construct the shear diagram by means of area. Area 1 is equal to because this is a load, so 1/2 negative 1/2 of quantity 12 plus 20 times 2, negative 32 kilonewtons. Then area 2 would be this trapezoid here, negative 1/2 of 20 plus 36 times 4 equals negative 112. And this is area 3, which is F3, negative 108. So there's no need to compute area 3. So this is the shear diagram. First, we go down by 15. So from 0 to negative 15, we have an abrupt change in shear. Then this is negative increasing coordinate or negative increasing ordinates, interpreted here as negative increasing slope. So it would be like that. So negative increasing slope, so negative 15. Then plus the area 1, which is negative 32, so we'll have negative 47, and the curve should be negative increasing because this is negative increasing intensity or ordinates of the load diagram. So negative 47, then plus RB, because we have shear here, minus negative 47 equals RB, and RB is 183.6, so negative 47 plus 183.6 is 136.6. Then we have here 20 to 36, that's positive increasing negatively. So it looks like this curve here. So it's second degree curve, then negative increasing. 136.6 plus area 2, which is negative 112, is equal to 24.6. Then after that, we have negative decreasing ordinates because W is negative, decreasing to 0. So the slope of the tangent here is horizontal, negative increasing like that. So 24.6 minus 108, because the area is 108, equal to F3, is equal to negative 83.4, then plus RD 83.4, so that closes the shear diagram. So next is the moment diagram. So let's find first this distance where shear is 0. So we will express the intensity of load here as, let's call that W, as function of x1. So if I call that x1, then this is 6 minus x1. That is also x1. So 6 minus x1. By similar triangles, W as to 6 minus x1 equals 36 as to 6. So the tangent at this point here, represented by this red dashed lines, center lines, is equal to the intensity of the load above, which is negative 12. Therefore, the vertical distance between the horizontal and this tangent here is supposedly tangent of this angle is equal to opposite over adjacent. But since the tangent of this angle is the slope of the tangent, which is negative 12, interpreted as the intensity of the load above, negative 12 times 2, so we have negative 24. So that I'll just put it 24 because it is in the negative side. So if this is 24 and 47 minus 15 is 32, meaning to say the height of this spandrel of parabola is 8. So that's 8. So that 8 plus 24 plus 15 is 47. Then just make it negative. So I'll call that area 3. So W as to 6 minus x1 equals 36 as to 6. So W is 6 times 6 minus x1, quantity 6 minus x1. So shear in CD is therefore equal to 24.6, there's 24.6 here, minus the area of this trapezoid. The area of the trapezoid is 1/2 quantity, 0.5 quantity, 36 plus W, and W is 6 quantity, 6 minus x1, times the distance between 36 and W, which is x1, equals 0. Because the shear is 0, we want to find x1. So that is 36 plus 36, 72, times negative 0.5, negative 36 of x1. Then 6 times negative x1, negative 6x1, times negative 0.5, positive 3 of x1 square, equals 0. So by quadratic equation, x1 is negative of negative 36 plus minus square root of negative 36 square minus 4 times a, which is 3, times c, which is 24.6 over 2 times a. So x1 is 0.7274 meters. So this assumes that you cannot use your high-tech calculator. So I use quadratic formula. So there are two values of x1, but this is the real value of x1, which is less than 6. The other value, you just compute it. And that is an absurd value. So having known x1, then we can now find the area 5 later. So let's call this area 4. Then again, the tangent at this shear curve is at this point, just to the right of B, is equal to the intensity of the load, which is negative 20. So negative 20 slope times distance 4, so this distance is 80. So again, to compute that 80 there, slope, which is equal to the intensity of the load, that's the definition. Slope of the point on the shear curve corresponds to the intensity of the load, which is in this case WB, negative 20 times 4, so that's 80. So this height of the spandrel, because this is a spandrel of parabola, is equal to 136.6 minus 80 minus 24.6. So that would be equal to 32. So again, 136.6 minus 80 minus 24.6 is 32. So we can now compute area 4 later. Then for area 5, area 4 is area of rectangle 4 by 136.6 minus area of triangle 1/2 of 4 times 80 minus area of spandrel 1/3 of 4 times 32. I hope you can understand that. So area 4 is equal to 343.733 kilonewton meter. Then for area 5, so let's enlarge this portion here. So remember that W is equal to 6 quantity 6 minus x1. So 6 times quantity 6 minus 0.72474, 31.636. But this is negative because that's a load. So if we enlarge that figure there and we draw the tangent to this point where shear is 0, the slope of this tangent is negative 31.636. And since the distance is 0.7274, so negative 31, or you just make it positive 31.636 because this is already the negative slope direction. 31.636 times 0.7274 is equal to the height of this triangle here. So 23.012. So therefore, the remaining height for the spandrel is 24.6 minus 23.012. So that's 1.588. And the whole area here is area 5. So area 5 therefore is area of triangle 1/2 of 0.7274 times 23.012 plus 1/3 of 0.7274 times 1.588. So area 5 is equal to 8.755 kilonewton meter. So knowing that, we can also compute this area 6 here. So this is the tangent extended, and the slope of the tangent is negative 31.636 times 5.2726. This is 5.2726. 5.2726. So negative 31.636 times 5.2726 is 166.804 negative. Then 166.804 minus 83.4 is 83.404, the height of the spandrel. So therefore, area 6 is area of triangle minus area of this spandrel. So negative of area 6 is, let's make everything positive. So 1/2 of 5.2726 times 166.804 area of triangle, this triangle here, minus area of spandrel, which is this, 1/3 of 5.2726 times height, 83.404. So area 6 is negative 293.16 kilonewton meter. So we can now plot the, by the way, area 3 is area of rectangle, 2 times negative 15, plus area of triangle, 1/2 of 2 times 24, plus area of spandrel, 1/3 of 2 times 8. And it is negative. I just make the areas positive, but we put negative here. Area 3 is negative 59.333 kilonewton meter. So we can now plot. So beginning with 0, then this is negative increasing. So negative increasing, same as that curvature there. So 0, then negative 59.333, negative increasing. Then this next is positive decreasing ordinate, positive decreasing slope. So negative 59.333 plus area 4, which is 343.733. So we have positive decreasing. The ordinate there would be 284.4. Then plus area 5, positive decreasing also. So same curvature, but it increases to 84.4 plus 8.755 is equal to 293.155. Then finally, 293.155 plus area 6, which is negative 293.16, the result is almost zero. And we have negative increasing because the ordinate is negative, but it is increasing negatively. So the curve or the slope of the curve should also be negative increasing slope. And that's almost zero there. So that's the moment diagram. So we have a point of inflection, the point where moment is zero, point of inflection. Let's extend it upward. Then in this portion here, since this is negative, the elastic curve is concave downward. It may be above or it may be below A, but it is important. The important thing is it is concave downward. Then for this portion here, because moment is positive, it is concave upward. And the elastic curve passes through the supports. Take note, because the supports do not settle or there's no displacement at the supports. So the other ways of computing areas are on the next slides, and the other technique of computing moments also. Will be presented. So remember, this is the elastic curve. Then let's recompute area 3, for example, by defining shear in section AB. Remember that the change in moment between 2 points is equal to the area of the shear diagram. So we have to establish or generalize the shear diagram. And assuming here that your high-tech calculator is available in computing or evaluating the integral. So I'll call that W. So W minus 12 as to X, this is X, equals 36 minus 12 is 24 as to 6. So W minus 12 as to X equals 36 minus 12 as to 6. So W is 12 plus 4X, or 4X plus 12. Therefore, the shear equation in AB is negative 15, then minus the area of the trapezoid, 1/2, negative 15 minus 1/2 of 12 plus 4X plus 12 times X, the area of the trapezoid. So simplifying, shear in AB is negative 15, 12 plus 12 is 24, divided by negative 2, negative 12 times X. So negative 15 minus 12X minus 2X squared, because 4X times X is 4X squared divided by 2, so 2X squared minus 2X squared. So moment at B minus moment at A is equal to area 3, and area 3 is integral of shear in AB dx from 0 to 2. So if you evaluate that, that is equal to area 3, which is negative 59.333 in decimal. So that's it. Or the other way, MB minus MA, which is 0, equals negative 59.333. That's why MB is negative 59.333. Next, MC minus MB equals the area of the shear diagram here. And if we use integration, then the better. The other way of computing MB is we consider section through B and consider all forces to the left, then we sum up moment about B. That's the other way. But let's proceed to BC first. So we have W1. Let's divide this trapezoid into two parts, rectangle and this triangle here. So W1, if this is XO, then this is 36 minus 20, because this is 20, 16 as to 4. So MB again is we sum up moment about B directly, considering forces to the left. So it is equal to negative 15 times 2 plus the moment of the 12 kilonewton per meter load, which is negative 12 times 2 times 1. Then the remaining moment of this triangle, remember the height is 8, because 20 minus 12 is 8 kilonewton per meter. So minus 1/2 of 2 times 8 times moment arm 1/3 of 2, or 2/3. So that's also negative 59.333 kilonewton meter. So W1 as to XO equals 16 as to 4, so W1 is equal to 4XO plus 20. So the shear equation in BC is equal to 136.6 minus the area of this trapezoid, 1/2 of quantity 20 plus W1, which is 20 plus 4XO, then quantity times XO, the distance between them. So simplifying, shear in BC is 136.6 minus 20XO minus 2XO squared. So computing for the area 4, which is MC minus MB, equals integral of shear BC dXO. Integral of shear BC times XO. That's the definition in our derivation for moment, shear moment construction. So it is 343.733 kilonewton meter square. You either use your calculator, high-tech calculator there, or evaluate these terms individually. That's only by power formula. So 343.733. So it verifies area 4 earlier by the area method and using the tangents to the shear curve. Then another way to compute moment at C is to take moment about C, sum up moments about C, considering all forces to the left. So since RB is 183.6 and RD is 83.4, so moment about C is 183.6 times 4 minus 15 times 6 minus 12 times 6 times 3 minus moment of this triangle 1/2 or 0.5 of 6 times 24, because 36 minus 12 is 24, times moment arm 2. So computing for MC, it's 284.4, just like this. Okay. And next, W2 as to 6 minus X2 equals 36 as to 6. So W2 is equal to 6 times 6 minus X2. So shear in CD is equal to 24.6 minus the area of this trapezoid, 1/2 of quantity 36 plus W2 times X2. So shear CD is 24.6 minus 36 X2 plus 6X2 squared. So evaluating M max minus MC, which is area 5, is equal to integral 0 to 0.7274, because we already found X sub 2 0.7274 in the preceding slides. So shear CD times dx2. So using your calculator or evaluating that individually, area 5 is equal to 8.755, just like before. Or the maximum moment, considering the forces to the right, is 83.4 times, this is 5.2726, minus the moment of this triangle, 1/2 of 5.2726 times W2, which is 6 times 6 minus 0.7274, or 5.2726 times moment arm 5.2726 over 3. So maximum moment is also 293.155, just like that. So that's it. And I hope that you know this technique. If not, then you have to enjoy the exploration of other ways of computing the moment or computing the areas. So use the definition of shear and moment. Okay, that's it.